Welcome to week 12 live discussion session of quantum chemistry of atoms and molecules. I'm October. I'm a PMRF at the Department of Chemistry in IIT Bombay. I am conducting these live discussion sessions for the last 12 weeks. As you can see, we are solving numerical problems on quantum chemistry. And we are also clearing doubts of the students, whatever they have, and we are also helping with the assignment problems. Today is the penultimate session. Actually, we are going to have a extra session on the 17th of October evening. On that day, also, I'm going to solve some numerical problems, obviously. But today's session, we will focus on the variational uh, theorem. Actually, which is an approximate method in the quantum chemistry. And last week we have discussed a few numerical problems on the perturbation theory. And the scope of the perturbation theory was that this uh, perturbation have to be applied onto some exactly solvable system whose wave function is well known, and then we do the rest of the calculation. But uh, uh, in case of variational theorem, that restriction is not there. You can choose any wave function or not any wave function. You cannot choose any arbitrary wave function, obviously. You have to choose a particular wave function which satisfied the condition of that whatever conditions are given for that particular system, and then you introduce a variational parameter into the trial wave function, and you try to vary the variational you try to vary the uh, trial wave function in such a manner that the energy of calculated energy of that states get closer to the actual value, and and that actually requires large number of iterations. So that is the main funda of you can say a variational theorem. But today actually we are going to discuss that assignment problem related to this variational theorem, and which is assignment 8. And then actually we are going to discuss assignment 11 actually to be specific. Uh, I'm not sure that if we are going to decide, we are going to solve assignment 10 and 11 and sorry 9 and 10 in the 17th of October, but we will see about that. Let us directly go to the uh, let us directly go to the assignment solution, and we will start solving the problems. So the first question states that if functional, this epsilon 05 actually known as functional, and this is actually given by, so if psi is your trial wave function, or let us here, as they are discussing about phi, so let us go with phi. So if phi is the trial wave function, then Hamiltonian, it will operate on the. So we are actually using the postulate where this measurement theorem was discussed. Right? So this is going to be your, this is known as your functional or the energy of the calculated energy. This is actually the method how we do get the expected value or expectation value of some operator. So some physical quantity. So here we are discussing about the energy, and then actually in your phi, in your trial wave function, there will be some variational parameter, and you vary that. So actually, as a upper limit theorem, that tells us actually this function will have to be greater than the greater than or equals to the actual energy. So D is going to be the correct answer for this. Now let us go to question number 2, there which states the in variational treatment of a quantum mechanical problem, out of these four, which are the correct option? Let us see. The system should be closed in energy to an exactly solvable system. This is not a stringent category, so I am not going to check this out. But what about the second statement? The first step is to choose a trial wave function whose value can be changed by varying a parameter. That is actually a correct answer because that is known as the trial wave function, right? So we have trial wave function, and that there is a variational parameter which you can vary. Now the third statement is large number of iteration lead to convergence towards the best possible values. That is also true for variational theorem. But option statement number four, greater number of parameters result in poorer fit. That is not a correct statement. So only second and the third statements are true for this question. Now let us go to question number three that states that while proving variational theorem, the trial wave function is expressed as a linear combination of wave functions that are necessarily be normalized and orthogonal. Actually orthonormal. So that actually so it was like that your trial wave function psi is C1 phi 1 plus C2 phi 2, suppose like that. Obviously, one can go with a higher number of shapes, but here what I am trying to do is suppose here it is only I to n, here I am going to I to 2. So your psi star, so if you work like this, obviously your variation is psi functional. C1 phi 1 C2 phi 2 A2 into 1 C1 phi alpha from the A2 into C1 P1 phi 1 plus C2 phi 2. Now here we are going to have C1 star C1 phi 1 phi 1 C1 star C phi 1 2 plus C2 C1 phi 2 phi 1 plus C2 C2 phi 2. See, and obviously same thing is going to happen in the numerator also. But what I was trying to say is that uh, uh, here we are going to use the orthonormal condition for each of these uh, phi 1 and phi 2. If you see, if this is going to be 1 and the cross terms are going to be 0. Okay, like that. Same thing we will do in the numerator also, and that is what is going to ultimately leads to that epsilon is going to be a greater than equals to the actual. So, so, so to give you an idea what this question is all about, I have just stated this here, and now we'll go to the next question. Now let us go to another question. That question states that for a particle in a box with infinitely large potential barriers at x is equal to 0 and x is equal to L. Obviously, this is, let me draw you the usual uh, particle in a box potential. So here the potential is infinity E from x is equal to 0 to L. So here you uh, just a minute. So here your trial wave function is given by phi of x is a product of f of x and g of x. Now the question states out of these four functions which cannot be f of x or g of x. So your phi of x have to, it cannot be arbitrary, right? It have to be something in terms of let me say that it uh, it should follow the boundary conditions obviously for the system. For right, your phi of x is equal to 0 should be 0 and phi of x is equal to L should be also 0. Now, uh, now if we go for suppose phi of x is equal to 0 is also 0, phi of x is equal to L is also 0. So for that case, your f of x or g of x either should be 0 or any one of them should be 0. So it's, so what I am trying to say is that your f of x is equal to 0 either can be 0 or uh, f of x L can be 0. Same goes for g of x as well. So we'll see for 3x x cube, when x is equal to 0, they are 0. So they are valid. Even for d, when x is equal to L, the function can become 0. But you, for x plus 3, at x is equal to 0, it is 3. And for x is equal to L, it is L plus 3. And L is a positive number. So it cannot be 0 anyway. So the correct answer is that it cannot be f of x or g of x cannot be x plus 3. They can be either other or others. Right? Now this question number 7. So before doing the question number 7, let me tell you this question has already been solved by Professor Datta in one of in the, I think, penultimate lecture of this week. Please, I'm not going to solve it here. Please look at that. Just I'm reading out the question that for a particle in a box using the trial wave function phi, that is a linear combination of f1 and f2, where c1 and c2 are the variational parameter obviously and F1 and F2 are given. Energy of the lowest energy level comes out to be B multiplied by H cut square by M, where B is. So let me give you the answer here. I'm not so if you remember that if you take the exact wave function for a particle in a box, which already we know that root over 2 by L sine n pi x by L. If you take that, then you are going to get 0.125. Then 0.000 after the decimals, right? So, and here you are going to, with this set of trial wave function and their linear combination, you are getting almost close to that. So that was the idea, that if you take a linear combination of several appropriate functions, then you are going to get closer in terms of energy. Still, your exactly solvable energy has actually exact energy is going to be lesser than this. Uh, that is all about the upper limit theorem, right? And actually, while doing taking this linear combination, it was also say that the concept of secular determinant was introduced, where your different terms like HII, HIJ, these terms are being discussed. And so I urge you to go through the lectures so that you that concept becomes clear, right? Because anyway, you are going to need the similar kind of concept of physical theory. But now let us go to the questions that I have curated from different. I guess this is from Macquarie Simon or Macquarie. I'm not exactly sure which book it is from. So these, I have here three numerical problems for variation in theorem from different books, and it actually have a rigorous uh, integration. It will require your concept of so you have to be very patient while solving the problem. And so let me read out the question, that we obtain the energy of the ground state of a one-dimensional simple harmonic oscillator using the trial wave function psi of x is equal to c exponential minus alpha x square, where c is the normalization constant and alpha is the variation of parameter. So psi of x is a trial function. Okay. So what the complex conjugate of this, that is going to be c star to the power minus alpha x square, right? There is no imaginary term. And one more thing, what is the Hamiltonian for a one-dimensional SH? First, the kinetic energy term, so minus h square by 2m d2 dx2 plus half m omega square x square. This is coming from the initial. Now, to start with, we need, as c is given as a normalization constant, so let us get the value of c. So that you can get when you integrate the, you take the normalization condition, that psi star psi dx is going to be 1. So let us take the constants outside, minus infinity to plus infinity, and it is going to become minus 2 alpha x square dx. That's equal to 1. See, for this we have given you a standard integral. So, but see here the limits is from 0 to infinity. But here it is not 0 to infinity, it is minus infinity to plus infinity. So what we are going to do here from now on is, we are going to, I am going to show you that how you can convert these to the standard integral and then take the this formula to get your answer. So see, minus infinity to infinity plus infinity e to the power minus 2 alpha x square. First of all, see, this e to the power minus 2 alpha x square is a even function. E to the power minus 2 alpha x square is even function, because even if you change the sign of x, f of minus x is going to be f of x. So that is one thing, and you can obviously break it as these are all related to summation, so you can break it down, right? Minus infinity to 0, 2 alpha x squared dx plus 0 to infinity, right? E to the power minus 2 alpha x squared. So you can break it down like that. And also what you can do is you can, if you have a minus, take a minus here sign, so you can flip the limits. The upper limit become lower limit and lower limit become upper limit. This part is remaining empty. Now, as this is an even function, so that's why we can actually going to write, we will be able to write this also as 0 to infinity. It actually going to give you 2 0 to infinity to minus 2 alpha x square dx. Okay, so it is actually going to give you c square multiplied by 2 0 to infinity e to the power minus 2 alpha x square into 1. You can satisfy yourself by easy one, the x square, right? Take a integration from minus 2 to plus 2 and you try to do it yourself. You break it down, you flip the limits. So x square is also even function. So you try to do it for you and you try to do check that if what I have just told is correct or not. At least this part, this minus thing, you can do it or not. Also, you can try it for a odd function. Anyway, now suppose now we are in the standard integral form. Not exactly, I will write it as 0 to infinity. Now there is, I can write x to the power 0, that is also 1. So I am writing it to match with the given uh, standard integral, and you will see that your n is 0 here. You can go with the even function, and your a is actually 2 alpha. So here you are going to have c square multiplied by 2 multiplied by minus 1 double factorial divided by 2 to the power 1 and then 2 alpha to the power 0 and pi by 2 alpha. Your a is 2 alpha, that is why I am writing pi by 2 alpha to the power half. That is equals to 1. And that leads to the 2 and 2 are going to cut, and minus 1 double factorial is actually 1. So c square, so you are going to have 2 alpha by pi half. Obviously c is big, and there are no negative things or something like that, so you can write 2 alpha by pi equal 4. And your wave function will be like 2 alpha by pi equal 0 e to the power minus 5. That is what it will be. Okay. Now you have your wave function. We have a wave function you receive, we know the value of the normalization constant. Now next one. Next is that we want to calculate the functional, that is your epsilon 0, and which is going to be dependent on this alpha, right? So that is nothing but from the measurement theory, that your it is going to be psi, with Hamiltonian psi, and denominator in bracket psi. Now your denominator, we already, your psi is normalized, so we don't, no need of writing the denominator. So we'll write only the this one. And from numerator, the let us take the first set of constant outside, that is 2 alpha by pi. It is going to be there 1 over 4, going to be there for twice. So we are writing it like this: 0 to, sorry, minus infinity to plus infinity. You e to the power minus alpha x square. Then obviously Hamiltonian is going to work on minus h square by 2 n d to dx2 on the e to the power minus alpha x square marks, right? And then half m omega square x square into, right? So first of all, we need to know the differentiation of this. Let us put here on this side, maybe where the the first of all, uh, we can write it down in terms of like the two time differentiation of d by dx. This part is going to be differentiation of e to the power, any exponential function is same as that. And what are the things going to come out? Obviously, minus alpha is going to come out. And uh, what is the integration of, sorry, differentiation of x square? So that is 2x. As a chain product, it came out. Right? Okay. So this is one step. And let me take the constant outside, that is minus 2 alpha. We are left with d of dx of x e to the power minus alpha x. So that is, so here we have two x dependent terms. So we are going to, once we are going to differentiate with respect to x, and this will be exponential term will be constant, and at one time we are going to make x as constant and differentiate it exponential term. So first let us differentiate x. So x, differentiation of x is a1. So we are only left with this exponential term, and now let's take x as constant, and we are going to have the same thing, 2 alpha x alpha x square. So we are going to have much more thing in common. So we are going to take those things out. X square, 1 here, and minus alpha x square. Okay. So we are going to put this value here. So we have outside the bracket by 5, half of that, then minus infinity to plus infinity, e to the power minus alpha x square. We have minus h cut square by 2. Obviously, this is constant. And then we have write it in this color. We have minus 2 alpha e to the power minus alpha x square 1 minus 2 alpha x square. Right? And we can close our bracket to dx. And we also have 2 alpha by 5 half minus infinity to plus infinity e to the power minus alpha x square half m omega square x square into minus alpha x square dx. Okay, so here we are again going to have, we should not do step jumps, else the chance of making a mistake. So right now we are trying to simplify the equation. So minus h cut square by 2am and plus 2 alpha actually going to become plus, so it is there. Then obviously 2 alpha is still a constant. Then we are going to have e to the power minus 2 alpha x square because there are two e to the power exponential function right and same, so they can add up. The order can add up 1 minus 2 alpha x square minus x square dx. 2 alpha x square dx. Then that part is done. Now let us see about this part. 2 alpha by 5. It will be easier to take the constant outside. You can do that. And we have x square alpha x square. If we can break this part even further, minus infinity plus infinity, and suppose I'm taking h square by 2 into the power 7, and then we are going to have the power minus 2 alpha x square dx once, and then h square by 2 multiplied by 2 alpha x square because 1 2 alpha was there and 2 alpha x square 2 alpha is there, so I'm giving twice. Then obviously we have alpha by 5 to the power half. Then these are all our constant now. Minus infinity x square e to the power minus 2 alpha x square x. And on this side we have the same thing. I have half square minus 20 plus x square e to the power x square dx. Now you will see here we have actually let me so these are all even functions inside the integrants. So obviously I am going to do the obvious thing what we are doing for till now. The h cut square by 2m into 2 alpha into 2 alpha by pi half into 2 minus infinity to infinity. Oh, sorry, I have made a mistake, right? I am trying to change the into so I have multiplied by 2, right? So I can now write it as 0 to infinity e to the power minus 2 alpha x squared dx. So this is one of the standard integral we have. Another thing what we are going to have minus h cut square by 2m. Let me write 4 alpha squared. We have 2 alpha by pi to the power half. And we are also this is a even function, so we can write 0 to infinity x square e to the power x. This side we have 2 alpha by pi half a omega square, and we can write if the integral is same, so same as the second one, x square x square. Okay, so we need to see that what are the values are going to be for uh, this integral, right? One of the integral is there are three integrals, so we can but we have to get the value of only for two because two of them are same. Let me highlight. I'm highlighting that two integrals for you. Okay? So we need to get these values for this, and we have this specific you can say this specific formulae, right? I can actually take this formulae to the particular side. Let me copy paste it to here. Maybe here. So, okay. So this is going to be accordingly to this. It is going to be 1 over 2 pi by 2 alpha to the power half. This we have done in the previous sessions. But what about this here? Here n is even and n is 2. So it is going to be a little different. It is going to be 2 minus 1, 1 double factorial, and then 2 to the power 2 by 2 plus 1, that is going to be 2 by 2, 2 to the power 2, then it is going to be 2 alpha to the power 1 because the n is 1, right? And it is 5 by 2 to the power half. Same for this, same for this means this is also 1 double factorial 2 to the power 2 alpha 5 by 2 alpha to the power half. So now what am going to do, I am going to let me delete this thing and then I will put my integration of all the things here only. The it starts by 2m into 2 alpha into 2 alpha by pi to the power half into 2 into this. Now I am going to minus h part square by 2m into 4 alpha square into 2 alpha by pi the power half into and I am going to calculate 2 alpha by pi half half m omega square into 2 into this. So you will see that if I take this green one, this pi by 2 alpha then is going to cut in all these three terms because they are like that. And then this we can cut this half to here. What about here? 1 factorial is 1, 1 factorial, 1 double factorial is also 1, 1 double factorial is 1, so we don't have to bother about that. What are the other things we can cut here? It is 2 alpha, it is 4 alpha square. So we can take this 4 out, we can take this 2 and this alpha we take here and this alpha square, right? What about here? Here these two can cancel out this, right? So let us see what we are ending up with. Here these two, these all gone, and we are left with these two also can move. So h cut square by alpha by m. Okay, first term. Then we have h cut square alpha h cut square alpha by 2m. Okay, and then on the third term we are going to have m omega square in numerator and in denominator we have 2 square 4 and then we have 8 alpha. Okay, and the rest of the terms are vanished, and these even we can simplify. The first two terms will lead to h square by alpha 2m plus m square 8 alpha. So that is your function. Now next step is to see that for which value of alpha it is going to give a break in the slope. So that can be done by the usual method that your d of this is going to be alpha your variational parameter 0. So that means that there is a break in the slope. And break in the slope can be either due to a maxima or minima. That can be even seen by using double differentiation, but that is not required here. You will see. So if we have d of d alpha H part square alpha minus or plus m omega square by 8 alpha, and that is here equating it to 0. So first h part square by 2m is going to be given from here. Then m omega square by 8 is constant. Then we have alpha. Therefore, minus 1 as a uh, yeah, and so yeah. So we can take h cut square by 2m on the side, and you can take square by 8 alpha square in the on the right hand side. And we can obviously exchange all the things. And this 2 and 8 will be 4. So alpha square I'm taking this side. So m square square 4 is square. So you see we are going to take the value of 5 m omega to h. So for this value of alpha is equal to omega by 2h cut, epsilon 0 is either maxima or minimum. We can find it out using a double differentiation, obviously. So, see the double differentiation of alpha is going to be a differentiation of the uh, h cut square by m plus h square by 8 alpha square. So the first term is going to be 0. Here we have square by 8, and alpha minus 2 is going to lead into minus 2 into alpha to the power minus 3. So obviously it is positive term. So square by 4. So any value of any positive value, any value. So if you put this value of alpha there, you are going to get your d2 d alpha to epsilon be positive. That tells us that actually now I can either maximum. So actually it is going to have a minima at that point. At minimum. So that we know it from here. So we can, and what is the minimum value that we can put the value of alpha there? H cut square by alpha 2 plus m omega square. So if we put the value of alpha is equal to m omega by 2h cross, so it is constant. Sorry, very well. M by 2h cut plus m omega square into omega. So see a lot of things will be cut off, which cross against M is going to cut, right? What about here? You know, omega cut. So 2 will 4. So we are going to actually left with h cut omega by 4 plus h cut omega and we will see that a0 minimum is h omega by 2 using the trial point function psi of a 2 alpha by pi 1 4 e to the power minus. Now if I have to write minus alpha x square, so I can directly write m omega by 2h cross x square, right? So this is your trial. These are the trial wave function we have taken, and that's why we are also getting the on the actual value also. See, so upper limit theorem tells us that from there we can get either the actual value or greater than that. So here we are getting the actual value of the ground state. You can see. So this is actually your ground state wave function that we are getting, and to be specific, we put the value to and to cut. So this is and actually you know that energy is E0. En is given by n plus half h cut omega. Right? So here it is 0 plus half h cut omega. That is h cut omega 2. So actually epsilon 0 what we are getting from here. Alpha is equal to h cross is actually equal to d0. Okay. So this we have done for one of the problem. Now we have the another problem. Another problem is almost the same. So we'll do it and let us see what is the value that we are going to get. Now try to read out the next question. The question states that for a one-dimensional simple harmonic oscillator, if one uses the trial wave function psi of x is equal to Cx e to the power minus alpha x square, where C is the normal constant and alpha is the variational parameter, then one obtains the exact energy of E is equal to 3 by 2 h cut omega for the fast excited state. So we are going to do the exact same thing like the previous one. So this will be a good practice for you to, if you can do it by yourself at your home, so this uh, will be a good practice. I will urge you to do it by yourself. So you're um, here we are going to prove it. Uh, so now our trial wave function is a little different than the others. So earlier we did not had this x inside, right? And doesn't really matter. If I do the normalization again, so we are going to get uh, let's see, and x square by x square dx, right? Is going to be 1, and from the previous case we know uh, the 2 so because this is wave function, and previous slide we have solved it for this particular integral, right? So that was the value was, see this particular integral what I'm trying to say. This we have solved for, that is 1 double factorial 2 to the power 2 to alpha 1 double factorial 2 to the power 2 into 2 alpha, right? These two and these two first. So alpha pi over 2 half. If I take this alpha inside of this, so it is going to become alpha cube, right? So really your C becomes your C square, let me write the next step. So alpha cube by pi equal half. So your C is actually 2 alpha cube by pi equal 1, right? Right? So your psi of x, actually let me take this equation maybe here. And you can put this here, right? You get much more space. So, so our trial wave function becomes 2 into 2 alpha cube by pi 1 over 4 x to the power minus 5 6. Now obviously we know the Hamiltonian. I will just again write it, minus h at square by 2m d2 dx2, okay, plus half m omega square x square. Now our functional is going to become functional is going to become psi, but we know this is normalized, so yeah, we have not to be worried about that. Okay, let me write it in the integral form. You can write it integral form, and obviously I will take the constant first set of constant outside, that is going to be alpha cubed by pi to the power 2. Then minus infinity plus infinity. First we have x and minus alpha x square. Then we have minus h square by 2a d2 dx2 of x into e to the power minus alpha x square, right? And then we have half m plus x square and x into e to the power x square and below. So first we need to calculate what the d2 dx2 of x into the power minus alpha x square is going to be. Obviously, we are going to do it two times. So first d of dx once, so e to the power minus alpha x square, right? From then the x become here and 2 alpha x is coming and actually minus 2 alpha x is going to come, so plus will become minus. So I will that. Now we are left with the this differentiation. This again is the first term is going to be minus 2 alpha x into the power six. Then actually we have d over dx of 2 alpha x square six, this one minus 2 alpha. Let me take common. We have x e to the power minus alpha x square. Okay, this side and the differentiation at this side at first with respect to 2x I'm going to be 2x x square is going to be 2x, which we have taken minus 2 alpha into that 2x e to the power minus alpha x square minus 2 alpha x square with plus 2 alpha x square then minus 2 alpha x. So let me take this thing here. I can take x e to the power in all those cases. I can take 2 x e to the power minus half x square as common. So minus 2 alpha was already outside and x e to the power x square. So this is 1. This is going to be 2. And here I'm going to minus 2 alpha x square and actually 4. 2 alpha was already come, so that was a mistake. So minus 2 alpha x square. So this is it. And the minus alpha x square. 2 alpha x square. So that I will complete here. So 4 into 2 by 5 half minus 20 plus 20 x into the power by square minus h square by 2m. Now I have my double differentiation value 2 alpha h into the power by square. So it's 2 alpha square plus half in omega square x cube e to the power minus alpha square. So that can be broken down into two parts, I guess. 2 alpha into alpha half infinity plus infinity minus h square by 2m alpha square x square x by x e to the power 4 e to the power minus 2 alpha x square minus. Okay, one was that. Another is going to be 4 2 alpha by 5 2 by 5 half minus 20 plus 20 now minus h plus square by 2a not 2 alpha square but 2 alpha then it is going to be our x square instead of x square minus alpha x square 2 alpha x square multiplied by minus 3 and b and the other term is going to be 4 3 alpha cubed by 5 because half minus infinity to plus infinity half in omega square to the power 4 e to the power minus 2 alpha x square dx. So I will write it in the next term. Next part will be d0 alpha is 4 into 2 alpha cube 2 alpha cube by 5 to the power half. But this is actually is common in all the things. So let me take a third bracket here. Then I have uh, minus h part square by 2m into 4 alpha square into, then I can write my standard integral, right? 2 into 0 to infinity x to the power 4 a to the power minus 3 alpha x square. This is one of the term. Then I am going to have plus h square by 2m into 2 alpha and c obviously, and then 2 into 0 to infinity x square e to the power minus 1 alpha x square plus half m omega square into 2 0 to infinity x to the power 4 e to the power minus 2 alpha x square. See, we now have again three integrals. So, and in these cases, standard integrals, you can see all this these are our, now we have in our standard format, right? I'm just highlighting the standard integrals, and we are going to use the formula on the right hand given in the right hand side. And don't worry, you don't have to remember this formula. You can do this given whenever is required, because we don't want you to mug up anything. They're all, so you have to do lengthy calculation, but you don't have to worry about mugging. If you have your concept clear, then totally okay. 4 2 alpha cubed by 5. So it is minus h cut square by 2m 4 alpha square. So it will integrate h alpha square. And this integral will lead to 3 double factorial 2 to the power 3 2 alpha to the power 2 5 2 alpha to the power half. In the second part, I am going to get h cut square by 2m into 12 alpha into this x. So this we know, this is 1 double factorial 2 over 2 into 2 alpha, and then 5. This is half to m omega square into 3 double factorial to the power cube 1 square 5 by 2. uh, So to make it easy, so let me take alpha outside, so it will become like something like that. And you see, this is going to cut with all of this inside. So I'm going to get 4 alpha here outside, inside square by 2m into 8 alpha square. C double factorial is going to be 3 into 1, that is 3, divided by 2 to the power 3 is 8, and here 4 alpha square. These already gone. Then that is going to be into 12 alpha into 1 uh, 4, 4 to the 8 alpha, then omega square, again 3 by 3 alpha square. So 4 alpha square and 8 alpha square is equal to 2 part. Then from here we have alpha 1, then 2, 2, 3, let us see, liquid. We have alpha here. Alpha minus square 3h part 2 square by 8 then this side we have 3h part square by 4m. This is actually in other terms. Anyway, let me continue. Plus 3m omega square by 32 alpha square, which is 4 alpha into 3h part square by 8m. 3m minus 3h part square of 2m 3 by 8 alpha. So now we have to see for which value of alpha b epsilon by dr will be 0. So from the first term, it's coming up as 3 square square by 2, then 3 8 plus 2 0 3 Three, three, one, two, is actually I have done it here. Sorry for that. It will do my best. Alpha square, square, square divided by 4 is m square omega square divided by 4. So again your alpha becomes m omega by 2h. And obviously if you check this double, so your epsilon 0 will have minimum alpha is equal to m omega by 2h square, right? So we put the value of that and to get the minimum energy, right? So let us put it. So your epsilon 0 alpha omega by 2h, that is c square by 2 omega by 8 into h by omega. So there h square on 4. Let's see what we are used to it. So let's do 3 h square omega by 4 by the ratio of h square by 4 h square by 2. So really your epsilon 0 minimum comes out to be this. So by to h square, here this is 3h square plus 2 is true. And this is what you have to do. So, and if you see, this is the exact energy for the fast excited state. So your wave function is 2, 2 alpha, 2 alpha by 5 to the power half, right? Multiplied by x, a to the power minus alpha x. So, let me write it here. 2 alpha by 5, it will not have 1 4. Uh, C is actually 2 alpha by x into the power minus alpha x square. So I need to put the values here. going to be 2 alpha is going to be uh, so I can actually write it as 2 alpha cube, right? 2 into 2 alpha cube is m cube omega cube. So this 2 into 2 4 cube, fourth, okay, and we are going to have a equal minus m omega by 2 h cross x square. So this is the actually the function. Okay. Now, actually, now we have another question. Using the trial of function, we have to see that your psi of r that is given, and now your alpha c is normalization constant obviously, and alpha is going to be variational parameter. We need to estimate the ground state energy of the hydrogen atom. First of all, you have your trial function c to the power alpha. So if you are going to use the normalization constant here, so actually here you have multiple things. You are going to have 0 to infinity for the r dependent part, that is going to be your t square a to the power minus 2 alpha r, right? And then you are going to have beta. Actually, let me make it little easy. So your integer could be psi star psi d tau could be 1. Now d tau is nothing but r square dr sin theta d theta d phi, because this is in polar coordinate, spherical polar coordinate. So that's what we are doing here. So this is 1. So so the c square minus 2 alpha r, and obviously d tau I will not write. Here I will write r square, right? R square dr. So this part is for r. What about the theta dependent part? Theta is going to be 0 to pi, right? Sin theta d theta. What about pi part? Pi can go for 0 to 2 pi d phi. So these actually leads to your one of the standard integral, right? So that it is going to give you, you can directly write this, that is going to give you 1 double factorial over 2 to the power 2 into derivative to alpha and pi by 2 alpha to half, and from this sine theta you are going to get minus cos theta, but you have 2 pi to 0, and here I will do 2 pi. So we have 1 over 8 alpha, then you have pi by 2 alpha to the half. From here you are going to get minus cos pi minus cos 0 and minus of minus cos plus. So actually you are going to get from 2 and 2 pi from here. So those are 3 you can cut here. So 2, 2, 4 to the 8. You can obviously take all of them inside. So it can become pi cube. Okay. And let me not do that. We have pi over 2 alpha. Okay, and that's interesting. We have pi over 2 alpha, here we have pi over 2 alpha. So actually, we have 1. So C 2 alpha pi C over 4, right? And this is going to be a normalization constant. So psi of I has become 2 alpha by pi. This is equal to pi. Okay, and now what is the Hamiltonian for your uh, hydrogen atom? So you need to. So let me, for time permit, let me give you this as a homework and try to solve this Hamiltonian. So that only depends on the R dependent part, right? So you try to get this done for the hydrogen atom. So this, please do it by yourself. We will try it on 17th of October. Don't do it. Homework. Keep it this as your homework. So let me actually eh, let me actually go to the next set of questions we have. Actually, we have assignment 11. Let us solve that. And the question states that the first question states that the molecular orbital theory uh, for H2 hydrogen actually overestimate the contribution of. You will see the answer is the ionic structure. Why? Why the ionic structure? That if you remember that uh, you are going to have the linear combination of two of the hydrogen atoms, right? C1H1 plus C2H2, and we will see that it is going to be almost 50% of the ionic structure. So, which is actually overestimating the ionic contribution of the trying to say. Now, question number two: if the bond angle is 105 degree and hybridization involved is SPH, then what is SPH? So here you can take some thing like when it is SP, then the bond angle is 180 degree, right? When SP2, the bond angle is uh, from 120 degree. When it is SP3, then it is close to 109. So obviously, if it is the bond angle is less than 109 degree, which is 105 degree, then it has to be X has to be greater than 3, right? But cannot be less than 2. So these options are not. X cannot be less than 1. X cannot be a uh, decimal, right? Decimal and less than 1, right? It can be decimal in some cases, but that is very arbitrary. Uh, Here it can be decimal, but it is actually more than 3. That's what we want to do. Hybrid orbitals are always be degenerate. That is not true. Delocalized over the molecule, highly directional, usually associated with payload. Actually, hybrid orbitals are highly directional. Okay, they're not delocalized over the molecule. That it's coming from the VBT field, and that is one of the problematic part of the VBT field. Anyway, question number four: that for an SPX hybrid orbital, this is given. Psi is given as a psi is given as a uh, function, or you can say this linear combination of these orbitals. Percentage of p orbital is going to be how many? First of all, one need to check that if all the contributions are uh, equals to the plus one, sorry one. So that is if the wave function is normalized or not. So one can do that. Take 0.625 square of it. Take some. Take plus with point uh, 312 square, then same for 0.417 square plus 0.625 square. Actually, that is going to lead to 1.05. That's okay. So what I'm trying to say is take sum of 0.625 square plus 0.3 square, and that this is going to lead to 1.05. So I'm not being bothered about much about this. It is almost close to 1. So percentage of P contribution. So what you can do that you can take the addition of this all, right, and take a square of it, or you can minus it from here, right? What I'm trying to say, if you 1 minus 0.625 square, it is leading to a 61%. Actually, uh, the S character is here is 40%, and even P character is going to be 61. S character is sorry 49%. Sorry 39%. 0.625 square, right? So percentage is said by that, so I shouldn't use the percentage, right? Okay. Now question number five, for sigma overlap between a 2s and 2p orbital, the plot of the overlap integral against the internuclear separation R is going to be as a maximum at R is equal to 0. So 2s orbital looks like your it has two nodes. It is spherical. Uh, we should not say it is orbital. It is the probability a surface, right? So plus and minus, and then your 2p will look like this, plus or minus. So you will see when the internuclear distance is zero, then or r is zero, then it is actually your overlap integral is zero, and it is also going to be zero at r equals to infinity. And these two are going to be the correct answer. Now, question number 6. Choose the incorrect statement from the following option. So the first statement, in bonding molecular orbital, electron density is low in the region between nuclei and bonded atoms. So this is actually incorrect. So I have to choose this because the electron density is high between the region between the nuclei and bonded atom, right? So this is the incorrect statement. Let us check the rest of the statements, that the energy of the antibonding molecular orbital is higher than that of the atomic orbitals from which it is formed. Obviously, that is correct. Your antibonding molecular orbitals raise higher in energy than the participant, uh, right? Orbitals. Then, what is the next? That every electron in bonding molecular orbital contributes towards the stability of the molecule. Correct. Antibonding takes place when the lobes of the atomic orbitals have different. That is also correct. So, only incorrect statement is the first one. Now, let us go to the question number 7. That the exchange integral raises the energy of a MO. No. Exchange integral lowers the energy of a MO. No. Actually, the fourth option is correct. It is a purely quantum mechanical quantity. Now, question number 8. According to the molecular orbital theory, the shape and size of a molecular orbital depends on shape and size of the combining atomic orbitals. Obviously, yes. Number of the atom combining atomic orbital, yes. The molecular orbital does depend. The shape and size does depend on the number of combining atomic atom. Size and shape, the first option, second option, and third. That orientation of the combining atomic orbital, that is also correct. So, the fourth option is all of them mentioned. So this is going to be correct. So I was thinking that for example, previously. So question number 9, if the sign of the wave function is unchanged when the orbital is deflected about its centers, then the a orbital is Girard, right? Now, question number 10, given below is the electron charge density of molecular orbital of hydrogen, now H2, identify the orbital type. The first orbital obviously has a node, right? And the second one doesn't have a node. So obviously second one is a bonding molecular orbital which rests in the lower energy, and the anti-bonding orbital, the first one, raises at the higher. So it is in the second of them. First is anti-bonding, second is bonding. Then one of the question I've taken from earlier thing, that in sp3 hybridization, what is going to be the contribution of each of the so what is going to be the correct statement in sp3 hybridization? So you can see each px, py, and pz orbital is necessarily 25%. That is not correct. They are actually all p orbital combined with 75%. So this is correct. Now s orbital can be a orbital 25%. That is correct. So these two are the correct answer here. Okay. Now, Um, we have maybe some more questions, but we don't have the time to continue. Maybe on 17th, I will discuss those questions. Let me share the questions with you right now, so that once you once we are done on the 17th, we can discuss this question. I have collected a few questions from here and there, uh, from the bonding molecular orbital theory and the variational theorem, hydrogen bond atoms, to try to solve these questions. Along with this, we'll solve some more questions. Anyway, today let us stop this session, and we will continue on the 17th of October. We will discuss some more numerical questions. That will be an extra session actually, but that is going to be our final session. So I thank you for uh, listening to this video and discussion session, and I hope it was useful to you. And with that, I'm going to end this session. I hope to meet you on the 17th of October evening. Thank you.